videos, as I have explained you about overview of Sentaurus TCAD. So in this video I am going to tell you about how to use this tool. So first of all I am going to call invoke the tool Sentaurus Workbench. How to do that? For that you have to log in, open your terminal, then you have to logged in using your ID. So in my case my ID is this one. Like you can use, if you have logged in earlier, then you can use the arrow key up and down for that purpose. So like this, for invoking the Sentaurus tool you have to, this one is your login ID, and you have to type SSH space slash underscore X space your ID at the rate 172.20.4.56 if you are using the OLAP facility in our institutions. So for that you have to logged in. After that you have to press enter so that you can enter your password, and now I am entering my password and press enter once again. Then something like this interface will come. So now directly I can do base, type base and press enter and sources, but in your case there will be one time directory making things, like, so the steps will be provided to you when you will get your ID. So accordingly you have to follow. So now I have to source my directory. For that purpose I will use my arrow key as I have logged in. So in your case you have to, after making the directory, you have to source it like this. You have to type source space slash linux underscore new slash scripts slash synopsis hyphen 2024. Now press enter. Then again you have to now you have to, like, for invoking the Sentaurus Workbench you have to type swb and percent. So swb and percent and press enter. So now the workbench will be opened. So this is the interface, Sentaurus Workbench interface, where you are going to use the STE and STWise tools as I have explained you in the earlier lecture. So you have to link your directory. For linking your directory you have to right click, then folder, then attach root and click OK. So now I am in my directory, and these are the some example files, or you can say I have make some devices in the software. uh, Login into your directory. Let's say we want to create a new project. For that you have to come to project, then click new, then after clicking new you have to come traditional project, then a error message will pop up, then you have to click OK. Then you have to source the location. So as for sourcing the location, as you have to first click in your in particular location where you want to create that file. So as I earlier I was on this node staff Pradeep, and then I click the projects and do the resting. So as you can see the tmt file in Sentaurus, when you create a new project then extension is .tmp file. So now recently I created a new project, so that file is 366077 underscore 0. So it is not like we are not able to find that file. So for that purpose you have to click save, and then again you have to source this and file this 36077. So 366607720 file, you have to double click on this and then OK. So now you have to just click and expand it, minimize and expand it. Now this is the your created file, glocalhost underscore 3668077 underscore 0.tmt file. You have to double click on it. Now this is the interface where we are going to add the HDE and HDevice tools. So for that purpose, for adding the tools, you have to right click on this area where it is written like no tools. So click on here, right click, then press add button. So add. Now come to this tools and search for HDE tools. So here it is HDE, and press OK, and select the run as batch mode. Okay, so it will uh, it is selected batch mode because whatever the file you are going to use, the simulation will be run according to your input file. That's why we are selecting batch mode. Then click apply and OK. So now you can see the HD tool is added in HWB workbench. Now another tool we have to add, that is HDevice. For that purpose you have to click right on this only HDE tool, right click on this, then add, then come to tools, then search for HDevice. Here you can see HDevice, then click OK, then apply and close it. Now in our HWB workbench there are two tools, HDE and HDevice, for the simulating the device. So now next thing is we have to input the files to these tools. For that purpose you have to right click on HDE, then edit, come to edit input and click commands. Then a gedit file will be open. A gedit file will HDE, you can see HDE underscore dvs.cmd file. So this is the space where you are going to input your HDE command files for the device. Now we have to source the HDevice tools also. So for that you have to right click on this tool, then come to edit input commands, then this is the area where you have to input your HDevice command lines. So this is the thing. And next thing is we have to add material parameters also in HDevice. So right click on this and edit, then come to parameter. Now you can see here the silicon is the default material for this Sentaurus ticket. So if you are not selecting for any parameter to any materials, then this workbench will select silicon as a default material parameters. So be specific for that. If you are using any other materials, then you have to select accordingly. So let it be like that and click OK. So this is, as you can see, this is the silicon parameter files for silicon materials. So these are the three command lines for these two tools. We have to input, or you can say we have to source it. So this is the thing. We are going to, from where we will get these command files for these two tools. So before explaining those things, like how to get these command files, I would like to show you a simulated version of the device for explaining purpose, and later on I will explain how to get these command files. So let's see the command files first. the project has been modified, do you want to save it? Yes. This message is for this project, so click yes. And now the simulated, yeah, this one. So the simulated version of this diode is here in front of us. So first of all, let's see the command lines for this STE tools. Let's close the earlier ones. So for that you have to come to edit input, then open commands. Then this is the command lines we are talking about to input in the STE tools. So how to get these command lines? To before explaining this, I'm going to explain this parameter file first. So you can see it is written as dimensions of p type. So you have to create like the dimension of the p regions. So for that, in SW in SDE tools you have to put the coordinates for making any shapes. So that's why it is like 0 0 x y g. These are the coordinates for making the device. So command lines is look like this. For p regions, this is the vertices by which rectangle will form for the p regions, and the material is silicon, as you can see, and the region naming is p regions. Similarly, dimensions of n type, this is the coordinates for making the shape of the device for n regions. This is the material and this is the region name. Then it means this is the these command lines are for making the device. Okay, next thing is doping of p type. So we have to dope the region also for making a p-n junctions. So for p type regions you have to dope boron active concentration, boron materials, right? And you have to give the concentration of also for that also, like what should be the concentration of the dopants in the silicon materials, right? So these are the command lines for that purpose. So these are like PR, p regions, boron active concentrations. They are using to for doping purpose, dopant materials, and this 1e plus 18 is the concentration level. Okay, so it means these two command lines are for uh, making a constant doping profiles in p and n region. Okay, next thing is we have to make contacts for the p-n junctions, right? We have to make anode and cathode. Like for the p context, p region context, you have to make a contact as a name of anode. You can give another name also accordingly. That is not a big issue, but you have to make contact, right? So for p region, making contact for p region, you have to make a anode, and for n region, you have to make cathode, right? So these command lines are for that purpose, and there will be, you can mention the RGB colors also. So 100 for anode and 101 for cathode. So as you can see, like current contact set, contact list, positions, you have to select the position where you want to make the contact. So these command lines are for making a contacts from this to this, right? So these command lines are for set contacts in p-n junction diode. Next thing will be we have to mesh the device for, so that physics and continuity equations, Poisson equations, or you can say differential equations should be solved in our device. For that purpose you have to mesh the device. So for meshing purpose, there must, it is a p-n junction, right? So you have to mesh the whole device, and another meshing should be in the depletion regions where the currents uh, maybe physics should be solved accurately in the depletion regions, right? So we have to create two meshing regions, one for one for the whole device, and the second one for the depletion regions or junction region, you can say. So for that purpose, these are the command lines to make sure the meshing should be done. And for whole regions, the meshing size should be coarse. You can do coarse meshing for the whole region, and but for the junction region you have to make a fine mesh to so that physics can should be solved. Okay, so these are the command lines for making the SDE uh, to for making the device PN junction in SDE tools. So these inputs, this should be the grid file for SWB. And next command line is as device tools. So for visualizing those, right click on it, then commands, and this is the like so as you can say, as you can see, there is a command lines grid in that is input files, and it is mentioned at the rate tdr at the rate. So this I was talking about the input file for as device, like SDE device command line. So these command lines are act as a grid file for as device tool, and it can be sourced by using these commands like grid equals to at the rate tdr dot. So for for sourcing this file to S device, we have to enter a, a command line in SDE device command line, that is this one, SDE build mesh n at the rate node at the rate. So this is the commands for making sure to source in this S device command files. For this SD device file act as a grid file for S device commands, right? So we have to put we have to have in our command lines this SD commands, right? So next thing is output files. So this one is as a act as a input files, and these files like plot, current, outputs are act as a output files for and the extension should be like at the rate tdr dat for plot, and current for current it will be like plot, and output will be in log scale, right? Next thing is electrodes. Yeah, so electrode name is case sensitive, so you have to take care of that. Whatever the contexts you have defined in SDE device command files, like I have means make a contact as anode and cathode for P and N regions. So accordingly we have to make electrodes name, right? So for making that you have to type anode and voltage, and you can enter some resistance also in series with electrodes, right? So for that I have mentioned. So these are the command lines for making electrodes and to link these commands with the SDE tool, right? Next thing is physics. Yeah, what the things we want to solve in our device in PN junctions, right? So we want Fermi levels in to visualize the Fermi levels in our device. We want that there must be recombinations and generation, I mean not generation, recombinations there. We want to solve Auger avalanche. uh, there must be electron mobility, doping dependence, high field saturations may be there, whole mobility, and for that also high field saturations will be there. So these are the some physics should be solved in our device, so we have to mention all those physics whatever we want to, that that physics should be solved. So we have to input it in our S device command files, right? Next thing is plot. What the things we want to plot from our PN junction diode. So we want density and currents, we want electron density, hole density, total current, right? We want to plot electron mobility, hole mobility. We want to plot field and charges like electric field, electron and hole field, space charge, electric potentials, what are the doping profiles in our device. We want to plot those things, right? We want to see generation and recombinations in our device. We want to see band to band surface recombination, Ioga, electron and hole avalanche. We want to see band structures like conduction band, valence band, current potential, electron and hole velocity, drift velocity, hole velocity, hole drift velocity, electron drift velocity. So these are the things we want to plot from our PN junctions. So all these things should be mentioned in our S device command file, right? Next thing is math sections. So these are the commands that should be in our file, so that this S device command, S device tool will be able to solve these uh, plots, right? Next is solve. We have a solve section, and these are the command lines for that purpose. uh, these are the quasi stationary. This is the main thing, like actually I can say like these are the important thing we are going through, and all these things should be there in our file. Otherwise, if you are saying like you are not having any solve sections, then how the volt you will be able in a position to vary the voltages, right? So all these command lines should be in there, and this one is the goal where we can vary the voltage. Like this is the anode electrode, right? And its voltage I have created variable. For making a variable, you have to make at the rate xyz at the rate things, so that you are able to make a variable and you can define the values of that variable. Like this, I have make a variable vs in hd command lines here, you can see, and I have given different values for that and simulated, right? So these are the things. There are a lot of things to explain in this file, but just I want to give you a overview that how the things look like in these command files, and these command files should be in our file. Okay, so I will come later on to explain this, that how we will be able to get these files by own. So you have to like you have to run first, right? You have to run it. To for running purpose, you have to click on this node and come to like run and just run. So I'm not going to do that, it will take a little bit time. Just you have to click OK and then it will run. So you can see here a lot of color codes are here, like qwait, ready, pending, running, done. So these colors are the states at where the our simulation is currently going on. So if it is yellow, it means our simulation has been completed. If it is this color, so then it will be, it means it is currently the simulation is being run in a running conditions. So these are the color codes, right? And these you can see this node and this virtual things, right? So it means this node is not being solved because there are another nodes for which we have made a variable vs and given it has been given different values -7, 23, 4 and 5. So these nodes are actual nodes, and this is like these are real nodes, and this one is complex or virtual node, you can say, like virtual node you can say, and it is not going to solve. So for visualization purpose, you have to click right, then come to visualize, then Sentaurus visual. Now you have to select the file. So as it is SDE tools, so it for there are two files, as I in the earlier lectures I have told you. SD from SD we are going to get two files. One is band dot n node number underscore band dot tdr, right? And another one was n node number underscore mesh msh.tdr file. So these are the two output files from SDE tools, right? So for visualization purpose, if you are going through this file band tdr and let's say what is inside this. So band.tdr I am selecting and click OK. So here visual will be opened, and this is the device structures we have made in HDE tools, right? So if you are going to click on this mesh, so this is the mesh which is not so good meshing you have done, because the meshing part is not included in TDR files, so that's why it is look like this. Okay, so it means dot band TDR file only shows the dimensions of the device, right? So let's close it, and now again visualize the mesh TDR file. So for that purpose you have to visualize Sentaurus visual, then click on mesh TDR and OK. Again Sentaurus visual will be opened, and now you can see earlier only dimensions were there, but now in mesh TDR we can see the doping concentration of this device also. And if you are going to click in this mesh node, then you can see clearly see the meshing part of the device we have done in the STE commands. So for whole regions meshing is coarse, you can see mesh size is bigger. For active regions mesh size is smaller. So you can see we have created two window for the meshing, right? So these are the things you can visualize the region wise, like n region and p region. So if you click n regions, so it means the p region is only here, so this is the p regions. If you click n region, this is the n regions, right? Okay, you can see the doping concentration of boron active concentration also. So for that just click this is, there is no any dopings in this case, but if when you click to boron active concentration, then you can see the concentration from 1e minus 30, that is closer to 0, it is going up to 1e plus 18, and concentration is boron, right? Now let's visualize the phosphorus active concentrations for the n region. So for n regions we have to click here, and it is also from 1e minus 30 to 1e plus 20. This is phosphorus for the n regions, right? So these are the doping concentrations. So it means that band TDR and mesh TDR files are being generated through the STE tools, and it look like this. Now next thing is, let's visualize the S device part. So for that I have simulated multiple values like -7, multiple anode values, multiple voltages you can say, like -7 volt, 20 volt, 3 volt, 4 volt, 5 volt. So let's visualize first 3 volt. For that you have to click 3 volt node, right click on it, then visualize, then Sentaurus visual. Now again you will get two files, one for the TDR device TDR file, and other one will be plot file. So device TDR file, as we have the grid it, I mean we have given a input file from SD to S device, that's why it is a device TDR. So I want to see, and device TDR contains the physical things, like you can see the electric field variations during the voltage variation or voltage biasing. So you can see the electric potentials, current flow in the device, and put and band to band recombinations, and space charge in our device. So all those things you can visualize through the device.tdr file. But I want to see electric characteristics, like I want to see IV, CV, those things can be visualized by device.plt files. So for that purpose you have to select device.plt, then click OK. Then again Sentaurus visual will be opened. Now the node 5 is opened, then Uh, for plotting the IV, you have, as we have varied the anode electrode, so we have to click anode, then outer voltage. Outer voltage will be go to x-axis, then total current variation will be go to the y-axis. Now you can clearly see the our IV from 0 to 3 volts, and the threshold voltage is nearly 0.7 volts in this silicon case, right? And you can see, or you can observe, the current is varying exponentially uh, with the variation of the voltage in x-axis, right? So this is the IV for simple diode, and this is the just overview part. Now I will explain how to get the command files for this SD tools, and how to get the command files for SDWise tools, right? So